Hello, welcome to Accurate Physics. In today's lecture, I'm explaining some key equations from momentum, impulse, and collisions. So first of all, we have to define momentum. Here we have a formula for momentum. The momentum of a particle is denoted by P and given by product of mass and particle's velocity. So P equal to mv. So it is a vector quantity because momentum have magnitude as well as its direction. That's why this is a vector quantity. The second formula is Newton's law in terms of momentum. We can express Newton's law in terms of momentum. Actually, this is a correct form of Newton's second law of motion. So in high school, we teach or we learn Newton's law is like F equal to ma. That is partially true. That is not completely true. So this law right here relates to Newton's second law in terms of momentum. The sum of the all forces that we can call the net force acting on a particle will be equal to the rate of change of momentum. dp by dt on the right hand side is rate of change of momentum. So the net force acting on a particle will be equal to the rate of change of particle's momentum. So this is the connection between Newton's second law of motion in terms of momentum. Okay. Third equation is about impulse of a constant net force. It is denoted by J and given by the product of net force, that is the constant net force acting on the particle, times the time interval. How long does it take to act that net force on a system or particle or a particle? Okay, so that is given by delta t, or t2 final time minus initial time, right? Delta t as a whole is a time interval over which net force acts on a particle. So this is impulse of a constant net force denoted by J. Like kinetic energy, work energy theorem in general, there is a impulse momentum theorem that connects impulse with momentum or change in momentum. On left hand side, we have momentum J, which is impulse of a net force over a time interval J. And on the right hand side, there is a change in momentum, which is delta P. Okay, so final momentum, delta P is simply final momentum minus initial momentum. So this equation connects impulse of a net force with momentum. So impulse is, in other form, we can express impulse as a change in momentum. Impulse is equal to delta P, or P2 minus P1. Okay, we already know the definition of impulse or formula of impulse, which is product of net force acting on a particle times the time interval taken to act. Impulse of general net force. So in previous formulas, we talked about constant force. So if force is not constant, what can we do? If force is varying, then we can use this formula. We have a calculus integration, right? So impulse of a general net force denoted by same letter J is equal to integration from T1 to T2 summation F dt, right? Net force acting on a system or particle times time interval of net force. So we can integrate from T1 to T2 because time is changing, the force is changing. The force is not constant, right? We can't apply the approach of constant force. The beauty of this approach using calculus is that we can use this formula for constant force, constant net force, as well as well as varying net force. If force is constant, we can take it out from integration sign and then just integrate dt. If force is varying with time, we can take force as a varying force and integrate as a whole. Total momentum of a system of particles, if there are more than one particles in the system, the total momentum can be obtained by simply adding, that is the vector sum of the momenta of all particles in the system. Let's say there are n particles, you simply add them up together to get total momentum of a system of particles. Let's say there are particles like A, B, C, D. So the individual momenta of the particles could be PA, PB, and PC, and so on. And total momentum P, represented by capital P, will be equal to PA plus PB plus so on. Okay, so which can again put in the form of mass times velocity, because the definition of momentum is mass times velocity. So how can you calculate the center of mass, the position vector of center of mass of a system of particles? The position vector of center of mass is represented by RCM. CM here means center of mass, right? R is a position vector, remember. So this is equal to, at numerator, you can say the product of individual masses, M1, and position vector of individual particles, right? R1. So R1, R2, R3, and so on. So these are the position vectors of individual particles. And a denominator, we have masses of individual particles, M1 plus M2 plus M3. So you can add all the masses together and divide it. So in other way, we can also write it down like summation Mi Ri divided by summation Mi. So this gives you the position vector of center of mass, RCM. This is very important equation to find out the position vector of center of mass. We can express the momentum in terms of center of mass, and that momentum, if you add all the masses together, all the masses of system of particles, we'll get total mass. And if you multiply the velocity, the velocity of center of mass, then you'll get the total momentum of the system of particles. That will be equal to momenta of individual particles, sum of the individual particles, right? So M1 B1 plus M2 B2 plus M3 B3, and so on. So which is equal to P, the total momentum of the system. Okay, so total momentum of the system can be equal to sum of the individual momenta of the individual particles, or the total mass of the system of the particles times the velocity of center of mass. And this is the finally key equation from this chapter. This gives you the net external force on a body or a collection of particles, which is summation F external, is equal to mass, the total mass of body or collection of particles, times acceleration of center of mass. Remember here, acceleration is not an acceleration of other particles other than center of mass, and other than the particle located at center of mass. So total mass times acceleration of center of mass gives you the net external force acting on a body or collection of particles. So I hope this is very useful lesson for you. If you are preparing for some test, the questions from this chapter can be answered if you know better about all these formulas. See you later.